Two particles P and Q of masses 4m kilograms and 3m kilograms respectively, they are at rest. They are at rest on a smooth horizontal ground. P is projected directly towards Q with speed 6.5 meters per second. Okay, so we have a horizontal ground. There are two particles, one is P and the other is Q. Let's represent them here, P and Q. P is projected at a speed of 6.5 meters per second. After the collision, they move in the same direction with speeds 2 and v. Show that v is equal to 6. Now, first part is fairly straightforward. This is conservation of momentum. We know about their speeds before collision. Before collision, P is moving at 6.5 meters per second. Q is at rest. We can consider the right side positive. If we consider the right side positive, then after collision, P moves in the same direction. So P and Q move in the same direction. The only possibility is that they move in the right direction, right? They move in the right direction. Because it's not possible that Q is at rest and P is moving to the right, that after collision, both of them start moving to the right, to the left side. That's not possible, right? So both particles are moving to the right after collision. After collision, we know the speed of P is 2 meters per second. Speed of Q is V. Apply conservation of momentum. We know the masses. This mass is 4m kilograms and this mass is 3m kilograms. Momentum before collision. That should equal momentum after collision. 4m into 6.5 plus 0. Momentum after collision, 4m into 2 plus 3m into v. M gets cancelled because that's appearing in every single term. So we get 4 into 6.5, which is 27, right? 27 equals 8 plus 3 times v. And that will give you the value for v. You can see what that is. 19 over 3. Is that what we're getting? There's something wrong there. 4m and there we had 3m, 8 plus 3v, 27. Let me see if I've copied values correctly. 6.5 there, 2 there, 26. That's a 4 into 6.5. I should probably just do that. I want a 6.5 into 4. That's 26. Okay, sorry. I wrote that as 27. 26. And then that gives us 18 over 3. There's still some problem with that, right? I need to check my working again. That's what happens when you get distracted in the middle. 4m, 3m. They were at rest initially. 6.5 meters per second is the velocity of P in the beginning. Okay, velocity of Q was 0. After collision, speed of P is 2 and speed of Q is what we have to figure out. Okay, so then I just input values here. 4m into 6.5 plus momentum of Q, that is then 4m into 2. Sorry?
6 आ रही है velocity सही तो आ रहा है
V equal to 6 आ रही है.
जी सर
Okay, yeah, V equal to 6 ही आ रहा है. I don't know what I was thinking. 18 divided by 3, that is 6. I had something else in my mind. V6 आ रहा है यहाँ से. That's, yeah, I'm sorry. I was doing some other division in my head. 18, मैं किससे divide कर रहा था 18 को? I was not getting 6. Okay. अच्छा. Let's move on to the next one now. Yes, I am also tired. It's okay. Chale. Given that the energy lost in the collision between P and Q is 45 joules, find the value of M. Given that the energy lost in the collision is this, find the value of M. Now, what's the initial energy? What's the initial energy? Initial energy. Potential energy will be the same, right? Because there's no change in potential energy. It's a horizontal surface. There's only change in kinetic energy. So that's the only energy that we consider for that reason. Initial kinetic energy in the very beginning. What is that? Half into mv squared for P. That will be half into 4m into 6.5 squared plus kinetic energy for Q, that will be 0. You can simplify this and that will give you 2 into 6.5 squared. I think I should just use a calculator now. 2 into 6.5 squared, or 84.5. 84.5 times m. Then what about the final kinetic energy at the end? Kinetic energy for P, that is half into 4m into 2 squared plus half into 3m into v squared. V value is 6. You input that there and you'll get some number from this as well. You can see what that is. What's this number? 8 plus 54, which is 62. Yeah, 62 times m. Now, they are saying the energy lost in the collision is 45 joules. Energy lost. Now, what's the difference in these two? 84.5 times m minus 62m. That should equal 45. And that will give you a value for m. You can see what that is. That turns out to be 2, right? 2. I would wait for a confirmation. Is it 2 kilograms? Yes? No? Yeah. Okay. M turns out to be 2 kilograms. ठीक है. Okay, there hasn't been a single difficult question in this paper until now. Let's look at this now. After Q has moved a distance of 9 meters from the point at which P and Q first collided, it hits a vertical wall perpendicular to the direction of motion of Q and rebounds. The speed of Q after hitting the wall is 0.5. Find the distance from the wall to the point at which the second collision between P and Q occurs. Okay, now this looks slightly tricky. Okay, so we knew nothing about their distances from the wall earlier. Now they're saying after Q has moved a distance of 9 meters from the point at which P and Q first collided, it hits a vertical wall perpendicular to the direction of motion of Q and rebounds. Let's make a vertical wall here. So let's suppose we've got this vertical wall and they were moving on a horizontal surface earlier. The point where they collided with each other earlier, they're saying that point is at a distance of 9 meters from that wall. Okay. The distance of that wall is 9 meters from the point of first collision. It rebounds. The speed of Q after hitting the wall is 0.5. Okay, so Q rebounds at a speed of 0.5 meters per second. Remember, the surface is smooth, so there's no decrease in speed while it is moving on the surface. Okay. Find the distance from the wall to the point at which the second collision between P and Q occurs. Okay, it's also not that complicated. If you have already done relative speed questions earlier, this is not the most difficult of those. How do we think about this now? Now, while Q moves to the right and reaches that wall, Q would also, P would also be moving to the right side. Let's figure out at what point P would be when Q collides with the wall. Okay. Now, what I'll do is I'll mark these points. I'll call this point something. Let's call this point X. And I'll call this point Y for now. X to Y. Let's consider consider what we know for this part of the journey. We know displacement, that is 9. We're talking about Q, right? Q, when it goes from X to Y, what do we know about that? Displacement, that is 9 meters, and the velocity, that is constant after that collision. Q was moving at a speed of 6 meters per second. So velocity is 6. We can find the time taken for Q to reach that wall. What's the time taken? It's constant speed, right? When speed is constant, we can just do distance over velocity, 9 over 6. Time taken for Q to hit the wall, that is 1.5 seconds. Time taken by P, or in fact by Q, until it hits the wall. Okay, that's the first thing that you figured out. Now, if this is the time taken when Q hits the wall, P would have also traveled some distance in that time. How much distance would P have traveled in that time? Let's figure that out. I'll do it on the side here. Let's call this point something as well in the middle until which P would have moved. Let's suppose this point here is Z. So for P, what's the distance x to Z? We want to figure that out. We know the velocity for P. What was the velocity for P? 2 meters per second after that first collision. So velocity was 2 meters per second. We also know the time taken now. Time is 1.5. Now Z is the point at which P would be when Q hits the wall. Let's find the displacement for this point. Velocity into time, and that gives us 3 meters. So that tells us that this distance is 3 meters. And if that is 3 meters, then what about the remaining distance? From this point to the wall, that is 6 meters. Now at this point, P is moving to the right at a speed of 2 meters per second. Q is moving to the left at a speed of 0.5 meters per second. P is going in this direction, Q is going in this direction. How much time would they take to cover this 6 meters distance? Let's figure that out. The time that we're looking for is the distance from the wall to the point at which second collision takes place. We're looking for distance. Okay. So now from this point onward, we can say the relative speed of the particles. What is that going to be? They're both moving in opposite directions. Every second, P is going 2 meters to the right and Q is going 0.5 meters to the left. What's the relative speed going to be? 2 plus 0.5, and that turns out to be 2.5 meters per second. That's the relative speed of the particles. Every second they're getting closer by a distance of 2.5 meters. So that's the relative speed. What's the time taken for this part of the journey? Can we find that time taken? 6 meters divided by 2.5. That will give you some value. You can see what this is. 6 over 2.5. What's this number? 2.4. 2.4 seconds. This is the time until the second collision. Time until second collision. After Q hits the wall. This is the time until second collision after P hits the wall. 2.4 seconds. Now that we have figured out this time taken, we are looking for the distance from the wall at which the second collision happens. Let's suppose the second collision happens somewhere around here. What is the distance traveled by Q in that time? Its speed was 0.5 meters per second. You can say distance traveled by Q until collision after hitting the wall. What would that be? The speed 0.5 into the time taken, speed into time, that will give you the distance 0.5 into 2.4, and that gives you 1.2 meters. This is where the second collision is going to happen. The distance from the wall of this point, whatever this point is, let's call this something as well, the point of collision, this point, distance from the wall of this point is 1.2 meters. That is what we were looking for. Make sense to everyone? For relative speed, do we always add the speeds? Do we always add the speeds? No, we don't always add the speeds. It depends on the directions. Let's suppose we have two objects going like this. One is going to the right by 6 meters per at 6 meters per second. Another is going to the left by 2 meters at 2 meters per second. Now, if they were 100 meters away from each other, every second they're getting closer by 8 meters. In this case, we would add those speeds when they're moving in opposite directions. If they're moving in the same direction, if A is moving to the right, B is also moving to the right, at what speed are they getting closer to each other? Every second, A moves to the right by 9 meters, B moves to the right by 4 meters. By how much distance do they come closer to each other? 9 minus 4, and that is 5. In this case, when they're moving in the same direction, the relative speed is going to be the difference between those two values. Make sense? Any issues with this? Okay, now let me repeat this part again, this last part again. Let me repeat this last part again. So what is it that they were asking about? They asked about the distance from the wall of the point at which the second collision happens. Now look at the different parts of the journey. Initially, P and Q were both here after the first collision. Now they said Q moves to the right by a distance of 9 meters until it hits the wall. Now, P would also travel some distance in that time. So firstly, what we're trying to figure out is at what point P would be when Q collides with the wall. Now, how do you figure that out? We are given the distance that Q travels and the speed at which Q travels that distance. From that, we can find the time taken until collision. Okay, time taken until it hits the wall, 1.5 seconds. Now, in those 1.5 seconds, how much would P have traveled? Its velocity was 2, time 1.5. It would have traveled 3 meters. So now, when Q collided with the wall, P was at this point here, such that the distance between P and Q was only 6 meters at this point. Now, from this point onward, P is moving to the right at 2 meters per second, Q is moving to the left at 0.5 meters per second. When will the collision happen? The collision will happen when this 6 meter distance between those two particles is covered. Now, how much time would it take for them to cover this distance? One is moving at a speed of 2 meters per second, another is moving at a speed of 0.5 meters per second. So every second they're getting closer by 2.5 meters per second. P is coming 2 to the right, Q is coming 0.5 to the left. We call this relative speed. Relative speed of these particles is 2.5 meters per second. Now, if the speed is 2.5, distance was 6, we get the time taken for the collision to happen, 2.4 seconds. Now, in that time, how much would have Q traveled? We just multiply the speed of Q, 0.5, with that time, and that gives us the distance that Q would have traveled, and therefore the distance from the wall when the collision happens. Is that okay? Makes sense, right? Yeah, so I explained that. When they're moving in the opposite direction, the relative speed is going to be their sum. When they're moving in the same direction, the relative speed is going to be their difference. Okay. A particle P of mass 0.1 kilograms is projected vertically upwards, with speed 30 meters per second. Mass is 0.1 kilograms, speed is 30 meters per second. At the same instant, a particle q of mass 0.4 kilograms is projected upwards with speed 10 meters per second. From a height of 15 meters above the ground, P and Q move in the same vertical line. Find the height above the ground at which P and Q collide. That's a standard kinematics question. You can make a rough sketch to understand the situation better. P is projected from ground at a speed of 30 meters per second. Its mass is 0.1 kilograms. Q is projected from a point 50 meters above the ground. So let's suppose we've got some building here, and Q is projected from there. It's already at a height of 15 meters above the ground. Okay, so Q is projected from here now at 10 meters per second. They are both in the same vertical line. I've represented them on the side, as in one on the left, one on the right, just to understand the situation better, but they're in the same vertical line, right? So Q is starting from this point in this direction like this. Now, at some point they collide. That means they would be at the same height. That is when the collision is going to happen, right? At some point they are going to be at the same height. We need to find that height at which the collision happens. Let's represent the information that we've got about both the particles, P and Q. Both are projected in the upwards direction. It could be two-way motion. Since they're projected in the upward direction, they might come downwards at some point. We will just consider upwards positive for both of them. Now, what about initial velocities? We know the initial velocities. Initial velocity for P is 30, for Q it is 10. What else do we know? We know acceleration. Acceleration is going to be negative 10, right? We're taking upwards positive. Gravity acts in the downwards direction. Gravity acts downwards. So acceleration is going to be negative 10 for both of them. What else? Is there anything else that we know about? Do we know final velocities at that point? No. Do we know time taken? No. Displacement, we have some information about displacement. What do we do now? What we think about what is common between them. Is there anything that is common between them? They both started from the same time. They started from the same time, and until they reach this height, they would have spent the same amount of time until that point, right? They would have spent the same amount of time until that point. So the time is common for them. If we consider the time of P to be T, the time for Q is also going to be T. So time is common between them. And we know something about displacement. What do we know about displacement? At the point of collision, we could say P would have traveled a distance which is SP, and Q would have traveled a distance which is SQ. We have a relation between SP and SQ. We can say SP is equal to SQ plus 15. We can make an equation like this, solve this equation, and find the value of T from this. All right. SP is equal to SQ plus 15. Now, which equation connects these things? U, A, T, and S. S equals UT plus half AT squared. Input values in that. For P, it will be 30 into T plus half into negative 10 into T squared. That equals 10 into T plus half into negative 10 into T squared plus 15. Simplify this, you get 30T minus 5T squared equals 10T minus 5T squared plus 15. 5T squared and 5T squared, they will get cancelled, and we're left with 20T equal to 15. The value of T turns out to be 0.75. This is the time after which the collision happens. Now, what's the distance above the ground, the height above the ground at which the collision happens, SP will be the height above the ground. We can find the value of SP now. Let's see what that turns out to be. Distance traveled, displacement of P from ground, that is given by this 30 into T, that is 0.75, plus half into A, which is negative 10 into 0.75 squared. That will be the height above the ground. You can see what that is. What's this number? Has anyone done this? 19.6875. Thank you. 19.6875. Round it off to three significant figures, and that will be 19.7. That's the distance that we were looking for. That's the height above the ground. Okay. Any issues with this? If it's an exact number, you just leave it as it is. Is it exact? Or is it rounded off 6875? Okay, so if it's exact, you leave it as it is. Then you don't need to round it off. You leave it as it is. If there was a large number of decimals which were not ending, then you round off to three significant figures. If it's exact, you leave it as it is. Or as a fraction, that will also be fine. Okay, sure. That was part A. Now they're saying, when P and Q collide, they coalesce. Find the speed of the combined particle at the instant it reaches the ground. Okay, now this is a complicated part. It looks like it. When we have kinematics and momentum together, that becomes slightly more complicated. Let's think about this now. I'll just copy that diagram from there. Okay, so this is what the situation was. Now I'll remove irrelevant information from there. So we don't care what happened before. All we care about is at the point the collision is happening, right? So actually just ignore the rest of it. Let's say that's the point at which the collision is happening. The height of that point, just remove all of that. The height where collision happens, we found that in the first part. That was 19.6875. What's the fraction value for that? 19.6875. 315 over 16. Okay, so this was 315 over 16 that you found in the previous part. So we could say this height is 315 over 16 meters above the ground at which collision happens. Now, what are their speeds at which the collision happens? At what speed, what are the speeds of both the particles? We would have to find that because we would need to apply conservation of momentum. Can we find their speeds before collision? Let's do that. Speeds before collision. Vp equals u plus at and vq equals u plus at. Initial velocity for p was 30. So 30 plus minus 10 into 0.75, that will give you 22.75, 22.25, no, 22.5. Yeah. And then VQ, it started at 10, so plus minus 10 into 0.75, and that will give you 2.5 meters per second. So at the point collision happens, P is moving at 22.5 meters per second in the upwards direction. And Q is moving at 2.5 meters per second in the upwards direction. So let's say this is P and this is Q. For Q, we know it is moving upwards at 2.5 meters per second. And for P, we know it is moving at 22.5 meters per second. That's before collision. They're both moving in the upwards direction. Can somebody confirm these calculations as well, please? They're both positive, right? And these are the numbers. Yes, considering both of them positive in the upwards direction, these are the numbers that you get, right? Okay. Now, we know before collision and after collision situation for both the particles before and after, we have particle P and particle Q. Let's consider upwards direction as positive. Before collision, we know the velocity of P is 22.5 and velocity of Q is 2.5. We know their masses as well. Mass of P was 0.1 and Q was 0.4. 0.1 kilograms and 0.4 kilograms. After collision, what happens is they coalesce and become one single object. So after collision now, they become one single object, PQ, let's say, the combined particle. Mass of this combined particle is going to be 0.5 kilograms. What about the speed of this combined particle? We can find that. Apply conservation of momentum. Momentum before collision, that equals momentum after collision. What's the momentum before collision? 0.1 into 22.5 plus 0.4 into 2.5. That equals 0.5 into VQ. And that will give you some value for VQ. You can see what that is. What's this number? 2.25 plus 1 divided by 0.5. 6.5. VQ turns out to be 6.5 meters per second. This is a positive number. Since it's a positive number, what that means is we took upwards positive. After collision, the combined particle is going to start moving in the upwards direction. Okay, it's going to start moving in the upwards direction. So now the situation is the collision has happened. Okay. After collision, the initial velocity of the combined particle, we have figured that out, that is 6.5. And in which direction is the particle moving? It is moving in the upwards direction since it's a positive number. So we can say the combined particle now, it's going to go up. Its journey is going to look like this now. It's going to go up for a while and then it's going to go down after that. Okay. This is ground. What information do we have about this particle now? We can consider upwards positive. It's two-way motion. When it's two-way motion in vertical direction, we consider upwards positive. Initial velocity, what's that? 6.5. And that's in the upward direction, so we consider this positive. What else do we know? Acceleration. If you're considering upwards positive, acceleration is going to be -10. Is there any other information that we've got? We know displacement. We know the point at which collision happened. That was 315/16. The point at which collision happened, that was 315/16. Okay, this is 315/16. So what's the value of displacement that we take here? Do we say 315/16? Is that the displacement value? 315/16? Will that be correct? Will this be correct or not? It'll be negative. We're considering upwards positive. We're considering upwards positive. This is the starting point. End point is down there. Displacement is to the in the downward direction. So the displacement value that we take is -315/6. And now what are we looking for? Speed of the combined particle when it reaches the ground, the final speed, that's what we're looking for. You can see which equation connects these four things. V square equals U square plus 2s, input values in that, and that will give you the result. V squared equals 6.5 squared plus 2 into A, which is -10, into S, which is -315/16. Input values in our calculator, see what value of V you get from that. You'll get plus minus, but it'll just take positive value because we're just considering the speed. Okay. 6.5 squared plus 2 into -10 into negative 315 over 16. And that will give you the result. That's 436. And then square root of that. Do we want an exact answer? No. So the speed turns out to be 20.88. To three significant figures, that will be 20.9 meters per second. And that's our final answer. Is that all right? Why is displacement negative? We talked about this yesterday as well. This is the starting point. This is the end point. Start, end. We are considering upwards positive. In which direction is displacement? From the starting point to the end point? Displacement is in the downward direction. End point is below, starting point is above. So overall displacement is in the downward direction. We considered upwards positive. So displacement is going to be negative. The second part. Now this seems to be difficult whenever you have kinematics and momentum, collisions happening. These questions tend to be among the most difficult. Let's see if that's the case with this question or not. Three particles P, Q, and R, they are of masses 0.6 kilograms, 0.4 kilograms, 0.8 kilograms. They are at rest. Distance from P to Q is 3 meters. Okay. And the distance from Q to R is also 3 meters. P is projected directly towards Q with speed 3 meters per second. P is projected towards Q with speed 3 meters per second. After they collide, P continues to move in the same direction with speed 1.5 meters per second. Find the speed of Q after collision. Okay, the first part is straightforward, just a simple application of Newton's conservation of momentum. So you write down what we know about before collision, what we know about after collision. We've got two particles, one is P and the other is Q. Considering the right side positive, P is moving at 3 meters per second to the right. Q is at rest at that point. After a collision, P continues in the same direction at 1.5 meters per second. We are looking for the velocity of Q. We have their masses as well. This is 0.6 kilograms and this is 0.4 kilograms. Apply conservation of momentum. Momentum before collision, that should equal momentum after collision. 0.6 into velocity of P plus 0.4 into 0. On the other side, we have 0.6 into 1.5 plus 0.4 into VQ. And that will give you the value for VQ. You can see what that is. 1.8 and then minus this from the other side. 0.6 into 1.5 is 0.9. That equals 0.4 VQ. 0.9 over 0.4. What's that? 9 over 4? That should be 2.25. That's the velocity that we get. Okay, that's the first part. This is all that we had to do. Okay, let's move on. Part 2. Now it says in the subsequent collision between Q and R, these particles coalesce. Find the speed of the combined particle after this collision. That's also straightforward. We have another collision now. Before this second collision, what do we know about both the particles? Before the second collision, Q and R, at what velocities are they moving? After the first collision, P is moving at 2.25. So that's the before collision speed. For the second collision, right? 2.25. R is at rest. So that is 0 meters per second. Afterwards, what happens is they coalesce and become a single object. Let's call that object, have they named it something? Let's call it C, the combined particle. We have to find the speed of this particle. Now, what about the masses? Q and R were 0.4 and 0.8 respectively. So this is 0.8 kilograms, this is 0.4 kilograms. So the total mass, what is that going to be? That will be 1.2 kilograms, sum of these two masses. Apply conservation of momentum. Momentum before collision, 0.8 into 2.25 plus the momentum of R, that is 0, equals momentum after collision 1.2 into velocity of the combined particle. And you can see what this turns out to be. 0.8 into 2.25 divided by 1.2. What's that number? What's this number, anyone? 0.75. This is the velocity that we get for the particle after collision, for the combined particle after collision, 0.75. Okay, that's our final answer. Let's move on. Okay, so first two parts were fairly straightforward. Now they're saying find the time that it takes from when P is initially projected until the instant at which P collides with the combined particle. Okay, now time from when P is initially projected until when P collides with the combined particle. So we've got two collisions already. And then they're saying P collides with the combined particle again after that. What's the total time that it takes? Achha, now, for this, we need to know a concept that some of you might not have done. It's just simple logic, but it helps to just do it in a bit of detail right now because we will need that for later papers as well. So let me actually go through that quickly. In recent papers, we have to use that quite a lot now. So what I've started doing is I've started teaching that as a standard thing now recently. Let me go through that. The concept of relative speed. Now it's simple logic, but let's just make sure that we understand it well. Let's suppose, let me actually hide this for now. There's a particle A that's moving to the right at a speed of 6 meters per second. Okay. There's another particle B that's moving to the left at a speed of 2 meters per second. The distance between them initially is 100 meters. Okay? That's the distance between the two particles initially at this in the beginning, 100 meters. Now, what's the time taken until collision happens, until they collide with each other? Now, the assumption is they're moving at constant velocities, right? If they were moving at different velocity, if the velocity was changing, if there was some acceleration or deceleration, then we would use our standard method. We would make some equation for A, make some equation for B, find their displacements, add them up and equate that to 100, like we do in kinematics, something like this, right? Make an equation, or not like this, but make an equation for displacement using S equals ut plus half at squared. Make an equation for displacement of B as well, similarly. Then you say SA plus SB equal to 100. That's the general method for such problems. But when it is constant speed, you can do it quickly in one single step. How exactly would you do that? If they're moving at constant speed, what's the time taken until collision? Think of it this way. Every second, how much distance is this particle A traveling? In 1 second, how much distance would A travel? It would travel a distance of 6 meters to the right in 1 second. Similarly, B would travel a distance of 2 meters to the left in 1 second. So in every second, A travels a distance of 6 meters to the right, B travels a distance of 2 meters to the left. Now, out of this 100 meters, how much distance is covered in 1 second? How much distance have they covered out of this 100 meters in 1 second? What's the distance now between them? 92 meters, right? They have come closer by 8 meter because A is moving 6 meter right. This is moving 2 meter left. So they have moved together at by 8 meters. This is something that we call relative speed. The speed of the particles relative to each other. And in this case, we can calculate it like this. We could say, let me bring that up from here now. Try that down here. Okay. What's the relative speed going to be then? we say the relative speed of the particles is 6 plus 2, which is 8 meters per second. That's the speed at which the two particles come closer to each other. Okay, so then to find the time until collision, all we have to do is distance over the speed, that's 12.5 seconds. And we would not have to make lengthy equations like these. We could do it directly in one single step, 100 over 8 like this. That's the idea of relative speed. Okay. Similarly, if they were moving in different directions, like this for instance, so A was moving to the right at 9 meters per second, B was moving to the right at 4 meters per second. How much time does it take for them to collide? Again, use the idea of relative speed. How much do they get closer to each other in 1 second? A goes to the right by 9 meters. B goes to the right by 4 meters. How much closer do they get? 5 meters. So they, out of this 100 meters, they cover a distance of 5 meters. So the relative speed in this case is going to be 9 minus 4, which is 5. When particles are moving in the same direction, the relative speed is going to be their difference, or the difference of their individual speeds. When they're moving in the opposite direction, the relative speed is going to be the sum of their individual speeds. Okay, now keep that in mind when we look at this problem now. So what was the situation? I'll just copy this diagram here. This is the initial situation of the particles P, Q, and R. There are three collisions that are happening. Let's see what's the time taken by all of those three collisions. This is the situation. Achha. Now, what about the first collision? So initially, we know P started moving to the right at a speed of 3 meters per second, right? Now, the distance is 3 meters. So what's the time until first collision? Time until first collision, we can find that, right? Time until first collision. What would that be? Distance over speed, that is 3 over 3, and that is 1 second. So until the first collision, 1 second passes. Okay? Achha. Now, P has reached this point after 1 second, remember? P is here at time equals 1. And its speed at time equals 1 is 3 meters per second. At this point, when P and Q collide, Q starts moving to the right side now. Q starts moving to the right side. Let me represent that here. Q starts moving to the right now. Q moves to the right at a speed of, what did we find there? 2.25. Now Q is moving to the right at 2.25. R is at rest. R is at rest. So how much time does it take to reach R now? What's the time taken for the second collision? You can say time between first and second collisions. What's that time going to be? That's again straightforward. Distance over speed, which is 3 over 2.25. You can see what that is. What's this number? 3 over 2.25? 1.33333. Okay, that's 4 over 3. 4 over 3, that's the time that we have between first and second collisions. Now, at the end, what happens is we have a combined particle. So now Q and R coalesce, they become this combined particle, and that combined particle is now moving to the right at a speed of 0.75 meters per second. And now the third collision has to happen. Between particle P and particle C. Okay. Now, what's the relative speed going to be? Remember, what speed is P moving at? After the first collision, P was moving at a speed of 1.5 meters per second. So that is still traveling at a speed of 1.5 meters per second to the right side. It's traveling at a speed of 1.5 meters per second. So we can find the relative speed now. 1.5 minus 0.75. But what about the distance value? What will be the distance that we take in that? Do we say P and C are going to be at a distance of 3 meters from each other? Do we use that distance? Or is it going to be something else? After the second collision, are P and C going to be 3 meters away from each other? No, because P continued moving in the right direction. P continued moving in the right direction while Q was moving towards R earlier. So in these 4 over 3 seconds that passed between the first and second collisions, P has also traveled some distance to the right side already. P was also moving in that time, right? So in those 4 over 3 seconds, when the second collision, while the second collision happened, P has already moved some distance. So you can say distance moved by P between first and second collisions. What would that be? How much distance does P travel in that time? Its speed was 1.5 meters per second. It travels the distance of 4 over, it takes 4 over 3 seconds. So 1.5 into 4 over 3, what is that? That is 2 meters. Yeah, that's 2 meters. That's the distance traveled by P between first and second collisions. So P is already somewhere here now. P has moved to the right and it has come to this point somewhere, let's say, such that this distance traveled by P while Q was going there, this is already 2 meters when this third collision happens. And now at this instant, what happens is P is moving to the right at a speed of 1.5 meters per second. C, the combined particle, is moving to the right at 0.75 meters per second. The distance between them is now only 1 meter. Out of that 3 meter, we have 1 meter left now. Now, what's the relative speed in this part now, in the last part? Relative speed of P with respect to C, what would that be? 1.5 minus 0.75, and that turns out to be 0.75 meters per second. What's the distance that it has to cover? Or in fact, time is what we're looking for. Time between second and third collisions, we can find that now. Time between second and third collisions, distance 1 divided by the speed, and that will give you the time taken for this part. 1 over 0.75, what's that number? That's also 4 over 3. And that's it. Now we can find the total time taken. Find the total time taken, see what that turns out to be. 1 plus 4 over 3 plus 4 over 3, and that gives us 11 over 3. Two particles P and Q of masses 2 m kilograms and m kilograms, they are held at rest in the same vertical line. The heights of P and Q above horizontal ground are at 1 meter and 2 meter respectively. P is projected vertically upward with speed 2 meters per second. At the same instant, Q is released from rest. Find the speed of each particle immediately before they collide. Okay, let's make a rough sketch to understand the situation better. We've got a horizontal surface, and there is one particle that is 1 meter above. Let's say that is here. That particle is P. There's another particle 2 meters above. That particle is Q. No, this is 1 meter. This is another 1 meter. Q starts from rest. It is released from rest. And P is projected vertically upwards with speed 2 meters per second at the same instant. We have their masses given, 2m kilograms and m kilograms. Find the speed of each particle immediately before they collide. Okay, now what does their journey look like? P is moving upwards, Q is moving downwards. At some point, they're going to collide with each other. Let's suppose that point is here. Let's call that point something. Let's say this is X. Let's write down the information that we've got for both the particles for P and for Q. P is moving in the upwards direction, so we can take upwards positive for that. Q is moving in the downward direction, we can take downwards positive for that. For P, we know, U is equal to 2, acceleration is negative 10, gravity acts downwards. We're taking upwards positive, so A will be negative 10 for this. Is there anything else that we know? There's nothing else that we know, right? What about Q? For Q, we know initial velocity is 0. What about acceleration? Gravity acts downwards. Mass is not required here, right? In kinematics, when we are applying constant acceleration formulas, mass does not have anything to do with them, right? We will have to use that when we use conservation of momentum later on. Because Q is released from rest. So it is moving in the downward direction, right? You can't release something from rest and it starts moving in the upward direction. That does not happen. So Q is going to move in the downward direction, right? When it is released. That's the only possible direction. Okay. What about acceleration? For Q, acceleration is going to be positive 10 because we're considering downwards positive. Gravity also acts downwards. So for Q, A is going to be positive 10. Now, we think of what else we can connect them with. Is there anything common between them? Is time common? Time is common, right? Because they both start from the same instant, and until the point of collision, the same time would have passed. Until the time of collision, the same amount of time would have passed. So time is common between them. So if TP is T, then TQ is also going to be T. Okay. Now, we also know something about displacement. The distance between P and Q was 1 meter. What that means is, until the point of collision, if P travels SP, then Q would have traveled SQ in the downward direction. We cannot assume that their displacements are going to be equal. Displacements are not equal. This will be wrong assumption that whatever distance P moves in the upwards direction, Q also moves the same distance in the downward direction. All we know is that the sum of SP and SQ that is equal to 1. This is all that we know. SP plus SQ, this is equal to 1. This is all that we know. Now we can make an equation using that. SP plus SQ is equal to 1. Which equation connects these things? S equals ut plus half at squared. Let's apply that on P. That will become 2 into T plus half into minus 10 into T squared. And then Q, 0 into T plus half into 10 T squared. That equals 1. Now let's simplify this. It becomes 2T minus 5T squared plus 5T squared equals 1. The value of T turns out to be 0.5. This is the time taken until collision. Okay. Now, what's the speed of each particle immediately before they collide? We can find final speed now, right? V equals u plus at. Apply that on P as well as on Q. Vp is going to equal u plus at. That means 2 plus minus 10 times 0.5, and that will give you minus 3 meters per second. VQ, U is 0 plus A, which is 10 into T, which is 0.5, and that will give you 0.5 into 10, which is 5 meters per second. That's the velocity of Q. Now they wanted us to find the speed of each particle. If we write -3, we lose a mark. We would say speed of P is equal to 3 meters per second, and speed of Q, that is equal to 5 meters per second. That's the first part that we wanted to solve. Fairly straightforward, standard kinematics question. This is what we had to do. Any problems? No? Now, there's an important thing to note here. For P, we took upwards positive. We took upwards positive for P. But its velocity is turning out to be -3. What does that mean? At the point of collision, P is moving in the downward direction. So what is happening here is P was projected in the upwards direction. Before it collided with Q, it had already started its return journey. It had started returning in the downward to the ground. Q was moving in the downward direction from the top. The collision happens when both of them are moving in the downward direction. Is that okay? So how is this still equal to 1? Because we're talking about displacement, right? So displacement doesn't care about what happened in the middle. All we care about is at the point of collision, P was this much above its starting point and Q was this much below its starting point. The sum of displacements is still going to be 1. Yes, the distance traveled for P is going to be greater, but that's not what we have in this equation. We have displacement in this. Displacement only cares about the current position of the particle. Okay. So at the point of collision, they are both moving in the downward direction. That is important to note from this result. Okay, now in the next part, they're saying it's given that immediately after the collision, the downward speed of Q is 3.5 meters per second. Find the speed of P at the instant that it reaches the ground. So now at the point of collision, we apply conservation of momentum. First of all, Q was above, right? That was also moving in the downward direction. P was below that. It's also moving in the downward direction. We know the speeds for both of them. Q was moving in the downward direction at 5 meters per second at the point of collision, and P was moving in the downward direction at 3 meters per second. Let's write this information on the side before collision and after collision. P and Q. Now we have to take one direction positive for all the objects when we're applying conservation of momentum. In kinematics, you see, I took upwards positive for P, downwards positive for Q. That's what you should do for kinematics. The direction in which the particles are moving, take that direction positive. But in momentum, we have to take the same direction positive for both objects. We can take downwards positive since both of them are moving downwards. Velocity of P is 3, velocity of Q is 5. Before collision. After collision, Q is moving at 3.5 meters per second. After collision, what's the speed of P? Let's call that Vp. Apply conservation of momentum. Momentum before collision, that should equal momentum after collision. We are given the mass of P was 2m kilograms, right? And mass of Q was n kilograms. Apply conservation of momentum. momentum of P before collision, that will be 2m into 3 plus momentum of Q, which is m times 5. That equals momentum after collision of P 2mvp plus m into 3.5. M is appearing in every single term, it will get cancelled out. And we're left with 6 plus 5, which is 11 on the left side. On the right, we've got 2vp plus 3.5. And that will give you a value for vp. You can see what that is. 7.5 divided by 2, which is 3 point... No. Is there something wrong there? 3.7 something, right? 3.75, is that what you're getting? 3.75, okay. Vp is 3.75 meters per second. And that's the value of velocity of P that we're getting. We need to find the speed of P at the instant it reaches the ground. So now what happens after collision? After collision, now P is at some point, it is moving in the downward direction at a speed of 3.75 meters per second. And it hits the ground at some point. Now, what do we know about this journey for P after collision? Again, we're taking downwards positive. Initial velocity is 3.75. Since we're taking downwards positive, acceleration is 10. We want to find the final speed. Time, we don't know what the time is. We don't know what displacement is. But can we find the value for displacement somehow? Is there a way to find the value of displacement? The collision happened at the point X, at this point X. That's where the collision happened, right? What's the height above ground at the point of collision? 1 meter this, and then SP more, displacement of P more. 1 plus SP. What we can do is we can find SP before collision first of all. Find SP first of all, before collision. That's this number, right? 2t minus 5t squared. Let's find that value. SP before collision. That is equal to 2t minus 5t squared. Right, we did that here. 2 into t, the value for t was 3.75. No, the value for t was 0.5. 2 into 0.5 plus 1 over 2 into minus 10 into 0.5 squared. That will give you something. What's this number? 1.25? How can it be 1.25? 0.25. Okay. Before collision, what was uh, the situation was like this. P started from here. This distance was already 1 meter. Q was here. Q was coming downwards. P was projected in the upwards direction. And then at some point collision happened. When we find the value for SP before collision, this value is turning out to be negative 0.25. Now, what does that mean? If this value is negative 0.25, we considered upwards positive for P there. If this displacement is negative, what is happening is the collision is actually happening down there like this. Q is coming down from there. P goes up for a while, then it starts going downwards. This is the point where they collide with each other, where P is below its starting point. So Q was coming from there. This is where they collide with each other, such that from the initial position, it is 0.25 meters below. This is where the collision is happening. Now, the earlier diagram was based on the information that we had available there. We just made a sketch of this, that okay, this is what it might look like. That was just for understanding the question. But our calculation is telling us the collision is not happening here. The collision is happening at some point when P has returned down there somewhere. That does not change anything before. All that changes now is, since the collision is happening below that initial point of projection for P, the height at the point of collision, what is that going to be? This height at the point of collision is 0.75. This is 0.75. So the displacement that we would use here would be 0.75 meters. It will be 0.75 meters. Okay. So let's find the final speed now. V squared equals U squared plus 2as. Input values in that. V squared equals 3.75 squared plus 2 into 10 into 0.75. And that will give you some value for B. I think I should be doing calculations myself thoughts that as well. Plus 2 into 10 into 0.75. Square root of this. That's 5.39. 5.39 meters per second. That's the speed of P when it hits the ground. This is why I keep stressing it is extremely important that you clearly write down what your positive direction is, and then accordingly you should be writing the correct signs for acceleration, displacement, time. Do not just change signs randomly. This displacement was turning out to be negative. It had a meaning. It meant that the collision point was below the starting point. That's what I've shown here, Musa. P was projected upwards. In the previous part, we already found at the point of collision, P was moving in the downward direction. So P went in the upwards direction for a while, and then it started moving in the downward direction. At the point the collision happened, P was below its initial position. So this yellow highlighted point, P is below its initial position. So the point of collision is below the initial position. It was at a height of 1 meter earlier. Collision happens 0.25 meters below that point. So how much does it still have to travel to reach ground after collision? It has to travel 0.75 meters below in the down after collision to reach ground. That is why we take displacement value as 0.25 there, 0.75 there.
Right.
जी उस्मान.
सर मैं ये पूछ रहा था, जैसे पिछले पार्ट में हमने डिस्प्लेसमेंट जो थी वो डिस्प्लेसमेंट का जो सम था पी और क्यू का, वो हमने 1 लिया था। तो अभी तो ये अगर ये -0.25 है तो ये तो 1 से बढ़ जाएगा यानी। तो
नहीं
पिछला
पड़ेगा,
पार्ट
नहीं पड़ेगा. Okay, so Q's displacement will be 1.25 now. Q की displacement 1.25 होगी, because for Q we were taking downwards positive. So Q has traveled a distance of 1.25 in the downward direction. For P, the displacement is negative 0.25. Add up both of them, 1.25 minus 0.25, that gives you 1. So the sum of displacements is still 1. As long as you're taking your signs correct, the sum is still going to turn out to be 1. Okay? Why did we not take initial velocity of P as negative 3 before collision in conservation of momentum? Let me repeat that. In kinematics, we can take different direction positive for different objects, and that is recommended. That will be more intuitive. P was moving in the upwards direction. P was projected in the upwards direction, so we can say it's two-way motion. In that case, we take upwards positive, right? So we took upwards positive for P initially. For Q, Q was released and it was moving in the downward direction. So for Q, we took downwards positive. From this, we got that this velocity of P was negative 3. Upwards was positive. Negative 3 means P is moving at 3 meters per second in the downward direction at the point of collision. For Q, we took downwards positive, and the velocity value was also positive. So for Q, we could say it is moving at 5 meters per second in the downward direction. When we applied conservation of momentum, we took downwards positive for both objects. Because in conservation of momentum, we have to take the same direction positive for all objects. Since we're inputting everything in a single equation, we can't take different directions positive when applying conservation of momentum. So here we're taking downwards positive for both of them. Both of them are moving downwards, so their velocities are positive. A particle A is projected vertically upwards from a point O with a speed of 80 meters per second. Okay. 1 second later, a second particle B with the same mass as A is projected vertically upwards from O with a speed of 100 meters per second. So we're projecting this from O at a speed of 80 meters per second. This particle is A. Another particle is projected from the same point and the same mass. That's particle B. And it is projected at 100 meters per second. This is projected 1 second later. Okay. At time t seconds after the first particle is projected, the two particles collide and coalesce to form a particle C. Show that t is equal to 3.5. The time at which collision happens. Now, let's say there is a point somewhere at which the two particles are going to collide with each other. Let's say this is that point. Now, the displacement until that point, is going to be the same for both of them. When they collide, until that point, A would have traveled the same amount of distance as B. Okay. Now let's write down what information we've got about both the particles about A and B. They're both projected in the upwards direction, right? So we can take upwards positive for both of them. For A, we know the initial velocity, that is 80. We know acceleration. We are taking upwards positive, so acceleration is going to be negative 10. And that's it. This is all the information that we've got for A. For B, we know initial velocity is 100 and acceleration is negative 10. Is there anything else that we can connect the two objects by, the two particles by? Is there anything that we can connect them by? Time, right? We know something about time. If we say the time taken for A is t, what about the time taken for B? What would that be? Time for B. B is projected later. The particle that starts later, it takes less time, right? The particle that starts later, it takes less time. For B, it is going to be t minus 1. That's a standard rule for time delay problems, right? The particle that starts later, it takes less time. The particle that starts earlier, it takes more time, right? I'll just explain that again. So you can think of numbers. For example, if A starts at time equal to 0 and reaches that point at time equals 10. Time equals 10 is, let's say, the point of collision. Now B starts 1 second later, let's say it starts at t equals 1. It reaches that point at time equals 10 as well. A takes 10 seconds. How much time does B take? 9 seconds. So B takes less time. If the end point is the same and the starting point for B is later, it would take less time. Okay? All right. So we'll have to consider that time as t minus 1. Now, we know something about displacements. At the point of collision, the displacement for both the particles are going to be equal to each other. SA equals SB. And that gives us ut plus half at squared, right? That's the equation that we can use. U is 80 into t plus half into a, which is negative 10 into t squared. That is equal to 100 into t minus 1 plus 1 over 2 into a, which is negative 10 into t minus 1 whole squared. Now we can solve this equation, find the value of t from this. The first one gives us, the left side gives us 80 minus 5t squared. The right side, when we simplify this, we get 100t minus 100. Can do some cancellation there, it becomes minus 5. Minus 5 into t squared minus 2t plus 1. Simplify this, you get 80t minus 5t squared. That equals 100t minus 100 minus 5t squared plus 10 times t minus 5. 5t squared and 5t squared, they get cancelled on both sides. On the right side, we have 110t that goes to the other side, minus 30t. On this side, we're left with minus 105. Right? And that will give the value for t, 105 over 30, that should give you 3.5. So the value of that capital T that they wanted us to find, that is 3.5. That's our final answer. Okay. Makes sense, right? How do we know it's free fall? How do we know it's free fall? Because the particle was projected vertically upwards. There is no resistance. If they don't tell us there is resistance, we assume there is no resistance. Okay. So weight is the only force. That means it's free fall. Okay. Now they're saying find the height above O at which the particles collide. Now that's straightforward. We know the time at which the collision happens. Height above O, we can find either SA or SB. That will be the height at which the collision happens. Could say height is equal to displacement of A. We already have the function for that. This one. AT into T. T is 3.5. Plus half into negative 10 into 3.5 squared. And that will give you something. What's the value that we get from this? 218.75. Is that an exact number? Yes, okay. So we can leave it as it is then. If it's an exact number, 218.75, that's the height. Okay. All right, let's move on now. Find the time from A being projected until C. What is C? Okay, they coalesce and become a combined particle C until C returns to O. Acha, we already know that until the time of collision, 3.5 seconds have passed. So that time we already know. So we are just concerned with what happens after collision. We need to find that time, right? Now, how do we think about this? We've also found the displacement from ground at the point of collision. That's 218.75. First of all, let's see what happens at the point of collision. Particle A was, we have to find the final velocities. Do we have them? No. Okay, so the first thing we should do is, to use conservation of momentum, we should figure out the velocities of both the particles immediately before collision, right? Immediately before collision, we need to find their velocities. Let's find them. VA and VB. What information do we have about both of them? For A, we know that initial velocity was 80. Acceleration was negative 10. We've also found displacement, that is 218.75. And we also know time, which is 3.5. So we've got all of this information. We want to find the final velocity. V equals U plus 80 will be fairly efficient. 80 plus minus 10 into 3.5, and that gives you 45 meters per second. That's the velocity at which A would be traveling just before collision. We can do the same thing for B as well. We know the initial velocity for A was 100. Displacement for this is also the same, although we don't need that. Acceleration is negative 10. What about time? Its time was t minus 1. That means 2.5. Find the final velocity for this. V equals U plus 80. 100 plus minus 10 into 2.5. And that gives us 75 meters per second. That's the velocity of B just before collision. Now, B was projected later. So at the point of collision, B will be below and A would be above, right? So what do we know about the particles now? We could say this is A. A was moving up at 45 meters per second, and B is at the same point as well, at the point of collision, and B is moving up at 75 meters per second. Let's write down what information we've got about before and after. Before collision, let's consider one direction positive. We can consider upwards positive. Before collision and after collision for A and B. If you're considering upwards positive, for A, initial velocity is 45, for B, it is 75. They're both going to be positive. After collision, they coalesce to form one single object. They said their masses are, yeah, so the masses are equal. Their masses are equal. So if this was m kilograms, this is also m kilograms. And what about the combined particle then, AB? Mass of AB would be sum of those two numbers, which is 2m kilograms. Let's say its velocity is VAB. In fact, they called it C. The combined particle, let's call it C. This is VC. Apply conservation of momentum. Momentum before collision should equal momentum after collision. What's the momentum before collision? M into 45 plus M into 75. That equals 2M into VC. M will get cancelled because it's appearing in every single term. And you'll get the speed of the combined particle 120 over 2, which is 60 meters per second. That's the speed of the combined particle right after collision. Okay, now what do we need to find out? We need to figure out the time until C now hits the ground. So the situation is like this. After collision, let's suppose C is here. It is at a height of 218.75. We don't need to break it. We can do it directly. We did similar questions in the last couple of classes as well. 218.75. If you want, you can break it down that it reaches a maximum point at some point find time taken for that, and then from the maximum point to the bottom. But it's not necessary for you to do that. You can do it directly. You can say, okay, its initial velocity is 60. It's going in the upwards direction. This is the starting point. It goes like this and then comes back at some point and hits the ground. Now, this is two-way motion. In two-way motion, we could consider upwards positive. So let's consider upwards positive for C. For the combined particle now, let's consider upwards direction positive. What's the initial velocity? We know that is 60 meters per second, at which it starts moving in the upwards direction now. U is equal to 60. What about acceleration? We are considering upwards positive. So acceleration is going to be negative 10 because gravity acts in the downwards direction. Acceleration will be negative 10. We're looking for time. What else do we know? This is the starting point and this is the end point. Upwards is what we are considering positive. Displacement is in the downward direction. The starting point is above, end point is below. So the displacement value is going to be negative 218.75. That's the displacement value. All right. Now you can find the time taken. S equals ut plus half at squared. Let's use that equation. Input values in this. Negative 218.75. That equals u, which is 60, plus half into negative 10 into t squared. Now we get a quadratic equation. 60t minus 5t squared, if I take all terms to the left side, that will give me 5t squared minus 60t minus 218.75 equal to 0. Put this in the quadratic formula. You need to show working for that. Cannot write down the answer directly. Minus into minus 60 plus minus square root of minus 60 whole squared minus 4 into 5 into negative 218.75 whole divided by 2 times 5. And that will give you two possible values of t. One is most likely going to be negative. Let's do that. Equation, you have those on the answers? Okay, thank you. 14.93 and negative 2.93. Now, negative is of course not possible. So this is the value that we use. What's the total time taken now? Since A was projected, 3.5 seconds had passed already before collision. So we can say now the total time taken is 14.93 plus 3.5, and that gives us 18.43, or we can say 18.423 significant figures. That's our final answer. Makes sense to everyone? Any questions on this? You see, we have seen similar questions in the last two papers as well, or at least at some point in the last week. So you should be able to do similar questions now, in which you have to use constant acceleration formulas in one part initially, and then collision happens, you use conservation of momentum in that, and then you have the combined particle moving again, use equations of motion again. Yeah, they're very similar, but lengthy at the same time. You would only be able to do them in the exam if you do a lot of practice of such questions. Otherwise, they take a lot of time, and time in M1 is pretty hard to manage. Okay, question number 7. It says a particle P of mass 0.2 kilograms is projected vertically upwards from horizontal ground with speed 25 meters per second. Show that the speed of P when it reaches 20 meters above the ground is 15 meters per second. Okay, so it's projected vertically upwards from horizontal ground. We can say upwards direction is positive. We know the initial velocity. Initial velocity is 25. What else do we know? Upward velocity is positive, right? Acceleration is going to be negative 10. When it reaches 20 meters above the ground, that means when the displacement is 20, we need to show that the speed is 15. So we have to find final velocity. V is what we're looking for. Now, which equation connects these four things? V squared equals u squared plus 2as. And that gives us 25 squared plus 2 into negative 10 into 20. And that will give the result. You can see what that is. Under root 225, which is 15. We get 15 from this. Yes? Okay. V equals 15. That's our final answer. Yeah, of course. Yeah. So we wanted to show that it's 15. And that's the final result. Achha, now they're saying when P reaches 20 meters above the ground, it collides with a second particle Q of mass 0.1 kilogram, which is moving downwards at 20 meters per second. P is brought to instantaneous rest in the collision. Find the velocity of Q immediately after the collision. Okay, now at that 20-meter point, we now know the velocity of this first particle, that was 15 meters per second. So at the point of collision, the situation is like this. There's this particle P that is moving in the upwards direction at a speed of 15 meters per second. And there's this particle Q that is moving at a speed of 20 meters per second in the downward direction. We've got their masses as well. Mass of P is 0.2 kilograms, mass of Q is 0.1 kilograms. This is 0.2 kilograms, and for Q it is 0.1 kilograms. We can use conservation of momentum. Take one direction as positive. Take one direction as positive. Which direction do we take positive? You can take upwards or downwards, doesn't matter. Let's take upwards positive. That's more intuitive since we have particles moving in both directions. If I take upwards positive, I can say the velocities before and after. Let's just summarize them here first. For P and Q, what are the velocities before collision? For P, the velocity is 15. For Q, the velocity is negative 20. After collision, P is brought to instantaneous rest. This velocity is 0. What's the velocity of Q just after collision? Let's use conservation of momentum. Momentum before collision, that should equal momentum after collision. Okay. Momentum before collision, mass of P, that is 0.2, into velocity of P before collision, that is 15, plus mass of Q, which is 0.2, 0.1, sorry, into velocity of Q, which is negative 20. That equals momentum of P, which is 0 after collision, plus momentum of Q, that's 0.1 times VQ. And that is going to give you the value for VQ. You can see what that is. On the left side, you get 1 or 10? 1. Okay. 1 equals 0.1 VQ, and the value of VQ, that is 10 meters per second. Is that okay? VQ is 10. Velocity of Q just after collision, that is 10. Now it's positive, that means it's moving in the upwards direction. Okay. After collision, just after collision, Q is moving in the upwards direction. Okay. Makes sense? Achha, let's look at the last part now. Find when P reaches the ground, it rebounds back directly upwards with half of the speed that it had immediately before hitting the ground. Okay. When P reaches the ground, it rebounds back directly upwards with half of the speed that it had immediately before hitting the ground. Find the height above the ground at which P and Q next collide. Okay. That looks a bit tricky now. Let's think about it. Achha, we had this horizontal ground. We had this horizontal ground. Now the situation is, we know just after collision, they are at a height of 20 meters, right? From the ground. Let's just confirm that. 20 meters above the ground. That was the height. Both the particles are at this height. After collision, what happens is P starts moving downwards, starting at a speed of 0 meters per second. Q starts moving upwards, starting at a speed of 10 meters per second. We found that in the previous part. Q is moving upwards at a speed of 10 meters per second. Now what happens is P reaches the ground and then it rebounds back directly upwards with half the speed of what it had immediately before the ground. Let's talk about P first of all and figure out at what speed it goes and hits the ground. Okay, let's try to figure that out. For P, we could say, the downward velocity, downward direction is positive. What do we know about P? U is equal to 0. Displacement is 20. It's free fall, right? We're taking downwards direction as positive. What's the value for acceleration going to be? Positive 10. So we can say acceleration is 10. Okay. Now we are looking for the final velocity. Let's find the final velocity. See what that turns out to be. V square equals U square plus 2as. Input values in this. 0 squared plus 2 into 10 into 20. And that gives us V equal to 20. This is the velocity at which P hits the ground. Velocity at which P hits the ground. Now, at what velocity does it bounce back? Half of that. Okay. It rebounds at half of that velocity. Okay. Now, we need to figure out the height above the ground at which P and Q next collide. Let's find the time taken for this as well, because we also need to figure out how much has Q moved in the upwards direction while P was, right? P was in the downward direction. While it was moving in the downward direction, Q would have also traveled some distance in the upwards direction. Now, how much has Q already traveled? We could find that. For that, we need the time that P takes to hit the ground. Now, how do you find that time? V equals U plus AT, we could use that. V is 20, initial velocity was 0, acceleration was 10 into t. So it takes 2 seconds for P to hit the ground. Q would have already traveled some distance in that time in the upwards direction. How much is that distance? Let's figure that out and do that on the right side here. Q was moving in the upwards direction. We can take upwards positive for that. Initial velocity for Q was 10. Acceleration would be negative 10 since we're taking upwards positive. Until P hits the ground, the time taken is 2 seconds. Let's find the displacement that it has already traveled in that time. S equals ut plus half at squared. We can say 10 into 2 plus half into minus 10 into t squared. You'll get some value from this. What's this value? What value do you get here? 0. Okay. So what's happening is, in those 2 seconds, Q goes upwards and comes back to the same position in that time. All right, so that makes it slightly easier than from this point onwards. SQ, we know that is going to be 0. If that is 0, can we also find the velocity at that point? If it's coming back to the same point, its velocity while going up was 10 meters per second. We could directly write that the velocity while going down, that will be negative 10 meters per second. So basically 10 meters per second in the downward direction. If you are not sure about that, you can evaluate that as well. The velocity of Q at that particular point, when 2 seconds have passed, let's find that. U plus 80, U was 10, in plus acceleration, which is negative 10, into time, which is 2. And that will give you VQ equal to negative 10. This is the velocity at which Q is moving when P hits the ground. So now we are at that stage at which P has already hit the ground and it is rebounding, and Q is moving in the downward direction. Okay. We are calculating time for Q. We're calculating time for Q because we need to figure out no, we're not calculating time for Q yet. Time for Q was already given, right? We are calculating displacement and final velocity for Q. We are finding the displacement of Q until the point when P hits the ground. So P hits the ground after 2 seconds. In that time, we're figuring out where Q is at that point and what its velocity is at that point. Now that we have figured it out, now it's a simpler problem and it looks like this. Q is here. I'm drawing that here again. After this point, now the situation is the particle Q is here and it is going to go downwards at a speed of 10 meters per second. Then P was at the ground. P was at the ground. It rebounds at a speed that is half of the speed at which it hit the ground. That's what the question said. So P is rebounding at a speed of 10 meters per second. So it's moving upwards at the speed of 10 meters per second. The displacement or the distance between the two particles that we've got at this point is 20 meters. This is all that we know. Now we again apply those formulas. This is the situation. Now we could say from this point onward, P and Q. P is moving upwards now. Let's take upwards positive for P. Q is moving downwards now. Let's move downwards. Let's take downwards positive for Q. What information do we have about both of them? For P, we know initial velocity is 10. Acceleration will be negative 10 because we're taking upwards positive. What else do we know? Nothing really. Let's write down the information that we've got about Q as well. What do we know about Q? About Q, we know initial velocity is 10. We are taking downwards positive for this. So acceleration will be positive 10 as well. These are two things that we know for both of them. Okay. Now, about the other quantities, is there anything common from among the other quantities? Time, they're starting at the same time instant in a way. And until the point of collision, both of them would have spent the same amount of time. from this point onward. Let's say this is the point of collision. So time is common. If we say time for P is T, then the time for Q is also going to be T. And we also know if Q is coming down by a distance of SQ and P is going up by a distance of SP, then the total of those two values is going to be 20. SP plus SQ, that is going to equal 20. And that is going to give us the time value for this part of the journey. SP plus SQ, that is equal to 20. Now, what is SP? SP is ut plus half at squared. That will be 10t plus half into minus 10 into t squared plus SQ. That will be 10 into t plus half into 10t squared. That equals 20. Now, these two terms get cancelled. They're both the same. And we get 20t equals to 20. And the value of t that we get from that is 1. So 2 seconds had already passed earlier. Then 1 second passes after that as well. What we want to do is we want to find the height above the ground. Okay, once we've got the value of t, I thought we were looking for time. No, we've found the value for t now. From this point onward, we can find the displacement of P now. The height above the ground at which this collision happens, this height, this is the same as the displacement of P. So we can find the displacement of P now from the ground. For P, we know initial velocity was 10, acceleration was negative 10. We also have the time value now. Just find the value of t. Ut plus half at squared, that will be 10 into 1 plus half into minus 10 into t squared, that will be 1 squared. And that will give you the result, which is 10 minus 5, and that is 5 meters. That's the height above the ground at which that next collision happens. That's what we were looking for.